Have you ever looked at a solar panel and wondered, how on earth do they make that? It looks like a simple, sleek sheet of dark glass, but behind that futuristic facade is a fascinating process that turns ordinary sand into a powerhouse of clean energy. Today we're going on an incredible journey from the beach to your rooftop to uncover the secrets behind how solar panels are made. Trust me, by the end of this, you'll look at the sun in a whole new way. It all starts with something surprisingly common: sand. But not just any sand. We need sand that's rich in quartz, which is a form of silicon dioxide. Silicon is the second most abundant element in the Earth's crust, right after oxygen, which is great news for solar energy. The first step is to mine this high-purity quartz sand and transport it to a processing facility. Here it's heated in an arc furnace to an incredible temperature of around 2000 degrees Celsius. This intense heat purifies the silicon, removing the oxygen and other impurities. What we're left with is called metallurgical-grade silicon, which is about 99% pure. Pretty pure, right? But for solar panels, we need to get even purer. This 99% pure silicon is good, but for electrons to move freely and generate electricity efficiently, we need to aim for what's known as 9/9 purity. That means 99.9% pure silicon. To achieve this, the metallurgical-grade silicon undergoes a complex chemical purification process, often the Siemens process. It's converted into a gaseous compound called trichlorosilane. This gas is then flowed over heated ultra-pure silicon rods. The silicon from the gas deposits onto the rods layer by layer, leaving almost all remaining impurities behind in the gas stream. The result is a big, chunky cylinder of polysilicon, which is the ultra-pure raw material for our solar cells. It's so pure that out of 1 billion atoms, only one is not a silicon atom. Now that we have our ultra-pure polysilicon, we need to turn it into something usable. We melt it down in a crucible at over 1400 degrees Celsius. From here, the process splits into two main paths depending on the type of solar cell we want to make: monocrystalline or polycrystalline. For high-efficiency monocrystalline cells, a tiny seed crystal is dipped into the molten silicon and slowly pulled upwards while rotating. As it pulls, the silicon atoms align themselves with the seed crystal, forming one single perfect crystal structure. This results in a cylindrical ingot that is incredibly uniform. For polycrystalline cells, the molten silicon is simply allowed to cool and solidify in a square mold. This creates multiple crystal structures within the ingot, which gives them that characteristic blue, marbled look you might have seen. Once the solid ingot, whether it's a single crystal or multi-crystal, has cooled down, it's time for some precision cutting. The big, heavy ingots are first squared off into long blocks. Then comes one of the most delicate steps: slicing the block into ultra-thin wafers. A high-tech wire saw, which uses a steel wire thinner than a human hair, coated with an abrasive material like diamond dust, slices through the ingot. It cuts hundreds of wafers simultaneously, each one thinner than a piece of paper, typically around 180 micrometers thick. This step is incredibly precise and requires a lot of care to minimize waste, as any silicon dust or kerf loss is lost material. These thin, fragile wafers are the foundation of our solar cell. So now we have these pure, raw silicon wafers. But on their own, they can't generate electricity. To turn them into a solar cell, we need to create what's called a p-n junction. This is the heart of how a solar cell works. Think of it like creating two different layers within the wafer. The majority of the wafer is doped with an element like boron, which has one less electron than silicon. This creates a p-type layer with an abundance of holes, or positive charge carriers. Then the top surface of the wafer is exposed to a phosphorus source at high temperatures. Phosphorus atoms diffuse into the silicon, creating a thin n-type layer. Since phosphorus has one more electron than silicon, this layer has an excess of free electrons or negative charge carriers. The boundary where these two layers meet is the p-n junction. When sunlight, which is made of photons, strikes the cell, it knocks electrons loose from their atoms in both layers. Because of the electric field created at the p-n junction, these free electrons are pushed towards the n-type layer, while the holes are pushed towards the p-type layer. This separation of charges creates a voltage difference across the cell. But how do we collect this electricity? First, to maximize the light absorbed, an anti-reflective coating, usually silicon nitride, is applied to the surface. This is what gives solar cells their typical dark blue or black color. It ensures that as little sunlight as possible bounces off. Then a grid of thin metallic contacts, usually made of silver paste, is screen printed onto the front surface. A full metal contact, usually aluminum, is applied to the back. These metal contacts act like highways, collecting the electrons from the N-type layer and the holes from the P-type layer, allowing the current to flow out of the cell and do useful work. We've successfully made a single solar cell, but one cell only produces about half a volt of electricity, which isn't enough to power much. To get a useful amount of power, we need to string them together. The individual cells are carefully arranged in a grid pattern. Thin metallic ribbons, or busbars, are soldered onto the front of one cell and the back of the next, connecting them in series. This adds up their voltages. Typically, 60 or 72 cells are linked together to create the power output needed for a standard residential solar panel. This matrix of interconnected cells is the engine of our solar panel. It's a delicate process, usually done by high-speed automated machines to ensure precision and consistency. Now we have our string of cells, but they're incredibly fragile. We need to protect them from the weather, impacts, and the test of time, because these panels are expected to last for over 25 years out in the elements. This is where encapsulation comes in. The cell matrix is carefully placed between two layers of a durable, transparent encapsulant material, most commonly a polymer called EV, which stands for ethylene vinyl acetate. On top of this sandwich goes a sheet of high transmission, low iron tempered glass. This is the tough outer shield that protects against hail, wind, and debris, while letting maximum sunlight through. On the bottom, a durable backsheet, often made of a polymer like Tedlar, is added to provide mechanical protection and electrical insulation from the back. The final step is to laminate this entire sandwich together. The layered assembly is placed into a lamination machine, which uses heat and vacuum pressure to melt the EVA layers. The vacuum removes all the air, and the heat fuses everything into a single, solid, weatherproof unit. The molten EVA flows into every nook and cranny, completely sealing the solar cells from moisture and air. Once cooled, this creates a rugged integrated module. To complete the panel, an aluminum frame is fitted around the edges for structural rigidity and to make mounting easier. Finally, a junction box is attached to the back. This is where the electrical connections are housed, including bypass diodes that help the panel perform better if a part of it is shaded. The panel is then cleaned and put through a series of rigorous quality tests, including a flash test to measure its actual power output and ensure it meets its rated specifications. And there you have it. From a handful of sand to a high-tech powerhouse. We've gone from mining quartz to creating ultra-pure silicon, slicing it into wafers, doping it to create a PN junction, adding contacts, stringing the cells together, and finally encapsulating it all into a durable, long-lasting solar panel, ready to be installed on a roof or in a solar farm. It's a journey of incredible chemistry, physics, and engineering. Every time you see a solar panel now, you'll know the amazing transformation it represents, a testament to human ingenuity and our quest for a cleaner, more sustainable future. Thank you so much for joining me on this deep dive today. If you found this journey as fascinating as I did, please hit that like button and consider subscribing for more content about the amazing technology that's shaping our world. Let me know in the comments what you'd like to see us explore next. Until then, stay curious.